Hey guys, my name's Trisha, and this video details my final project for Dr. Mitchell's class, ENME 489Y. The overall goal of this project was to render a 3D point cloud of campus one structure at a time. This was done by deploying our individual LiDAR sensors to map and collect images from any selected target. We then took these images and were able to generate a 3D point cloud from which we analyzed and processed the data to render a discernible mesh. The target that I chose to map was the Tau Beta Pi bend. The Tau Beta Pi statue is located in front of Martin Hall, closer to the entrance to Resnick Lecture Hall. So I chose to map this particular object for two reasons. One, I'm in Tau Beta Pi, and two, I thought the geometry of the overall structure would be pretty interesting to recreate. So the top is made up of some sort of metallic brass material and is pretty geometric in its profile. The bottom is also geometric and is made up of some sort of concrete mixture. The bottom cube base has sloped faces on both the rear and the front, and the top is mostly made up of just angles and straight lines. The only exceptions at the very top of the statue where there's a keyring looking fixture, and it would be interesting to recreate the curvature on this. This is my overall LiDAR sensor configuration. To sensor map something, you need both a transmitter and a receiver. The transmitter here is the red line laser affixed to the bottom of this mount. The receiver is the Pi camera, which is mounted at the top of the mount. For the base, I chose to use the provided STL files for the 3D printed mount. There was slight warping in this print, but it still maintained the proper separation distance and dimensions. The base was then bolted onto a tripod for stability, as you can see in this video. A lot of the individual components were fixed to the mount using a variety of methods, so either tape, zip ties, or even just twisting spare electrical wire. My original sensor configuration used the Arduino accelerometer chip, but based on the results of earlier homework assignments, I realized that the offset angle calibration was causing my data to become skewed. From there, I switched to using a bubble level app on my phone, which you can see attached to the backside of the base. A lot of the technical operations of the sensor design will be discussed later on in this video. So what exactly is remote sensing? Remote sensing is the collection of information about an object without making physical contact with it. LiDAR is a specific type of remote sensing and stands for light detection and ranging. Basically, it uses light as the radiation medium for transmitting data. The governing equation for LiDAR is shown at the bottom here. N refers to the number of photons either emitted or received. At the interaction point, losses are seen due to the scattering coefficient beta and the range distance r. The photons received are then affected by the overall area of the receiving surface and the range distance again. Further losses occur due to the transmission in the medium, T, and the overall efficiency, eta. In my setup, the line laser transmits photons to the bent, which then reflects them back towards the camera. The camera takes an image of this reflection and continues this loop based on the computer feedback. In our design, we are relying on computer vision techniques to extract the object data. Computer vision is basically the analysis process and extracting of data from images. So is LiDAR active or passive sensing? Active sensing relies on self-generated radiation, whereas passive sensing utilizes naturally occurring or ambient sources, such as sunlight. Since LiDAR needs returns from transmitted light, it is active sensing. Depending on how far away the target is, the returns appear at a different pixel location on the screen. Tracking these pixel locations of the laser returns and backsolving for the distance is then how the coordinates are generated. Prior to the actual mapping, this relationship needed to be calibrated. This was done by both using a single point laser and a line laser and physically measuring the distances. Comparing the theoretical and experimental data then gives a good idea of how accurate the system is. The resulting calibration curves revealed that my system was pretty accurate after I made the necessary changes to the input values shown. The images that the camera then takes are processed using Python and the OpenCV class. OpenCV allows for the manipulation and processing of images, allowing me to mask the images based on selected HSV values. This then isolates the pixels of interest and allows me to select what needs to be processed. I chose to map the bent by sweeping the sensor up and down and orienting the laser horizontally. The mapping was done in 4 parts, one for each of the different faces of the bent. My laser was powered by an Arduino, which was powered by either an external battery pack or my laptop. My Pi was powered to a separate battery pack. The steps involved me running the data collection Python script on the Pi terminal and inputting the IMU angle read from the phone app. The camera then takes a picture which gets saved to the Raspberry Pi. The laser reflected pretty well from the statue, both the base and the trestle on top. You can see them with the naked eye in this photo. To maintain the same distance from the left and right face, I had to get in the mulch a bit, which was even further exacerbated on the backside. For the most part, the surrounding lights didn't detract too much from the clarity of the returns. If anything, it seems the cylindrical surfaces of the bent, such as the bottom and top support, were poor reflectors as their surfaces were not fully normal to the camera. Some issues I ran into while recording data included the mulch incline in the back face. This was the only way to get enough of a separation distance with the actual object, and it just involved me changing the height of my tripod legs. Furthermore, when you're mapping the back face of the bent, you're shining the laser directly into the street. This is pretty problematic when you have cars driving past, as you can see in this top frame. Furthermore, another source of issues was this lamppost right here. So when you're filming the right face of the bent, the lamppost provides noise in the background of the image, which actually didn't seem to impact the resulting point cloud that I'll show later. However, when you're filming the left side of the bent, the lamppost makes the really reflective surface of the bent reflect that light directly, and as a result, it kind of drowns out the reflection of the laser. One thing I had kind of forgotten about was that Tau Beta Pi shines the bent every single semester, and I had just mapped on the shiniest point the bent would ever be. One way to circumvent that was that I would just move my head to create a shadow on that point on the bent, and thus make the red line seem more apparent. Once all the images have been recorded, we can then begin the processing of this data. So all the images I saved to separate folders regarding their orientation. So these were all of the measurements for the left side bent shown here. This folder is then what is read into PyCharm and the Python code. So the data generation code takes all of these pictures and these saved angle numbers and then applies a mask to pull out the relevant laser returns. So this code starts off by loading all of the preset values. As you can see, these were part of the calibration curve. It then goes on to load in all of the angle values. So the IMU angle that was inputted in the Python script on the Pi was saved as the file name and is then read in again here. The Python code in PyCharm then blurs the image, and based on the set HSV values, it creates a mask. That mask is then what helps to define what are red pixels for the returns and what are not. From there, it then determines the pixel location and goes on to append this into a matrix for the X, Y, and Z coordinates. After that, you get a resulting text file which has the 3D point cloud. That is then inputted into MATLAB over here, up at the top. So there was a point cloud for all of the 4 different faces because it had to be run for that. One thing to note, though, is that for the 4 faces, the left and right faces required different HSV values, and that was found by running this color picker code right here. The color picker code required the terminal execution shown at the bottom, so the file had to be stored within the same directory or folder, and you can just execute it with whichever picture. So I would just choose one image on random that had the worst returns, and then just determine what HSV values were relevant for that. Going back to the MATLAB code, I filtered the data from each of the data sets just based on simple conditional statements, whether or not that data was considered an outlier or just well out of reach of what surface I'm looking at. So I did that for all 4 of the faces. I didn't really filter the data beyond that or add any smoothing functions. I then went on and rotated the data, so when you're mapping, you're only mapping one face relative to the camera. It's not exactly representative of the orientation of all the faces. So I just rotated it about the z-axis. For the back face, I also needed to rotate it about the x-axis just because it was slightly tilted, and I think that was due to the tripod being uneven. The front face was set as a standard, so that didn't really need to be rotated. I also translated the right, left, and back faces. Once you rotate it, you exacerbate any deviations or translations offset, and so those need to be placed. I chose these translation numbers just based on playing around with a point cloud. So I would try to find shared features, such as, let's say, two corners, and just try to match those two corners based on selecting their X, Y, and Z coordinates, and I can show that later. I then appended everything into one total matrix variable, and then did a final cleanup and wrote that to a text file. Once you plot it, the resulting point cloud looks like this. As you can see, it pretty much looks like the tau beta pi bent. What I meant by choosing points is just a feature like this. You can click on it and it would show you the X, Y, and Z coordinates that are relevant. You can see each of the four faces of the bent, the front, left, right, and back, and you can see the overall profile of the trestle on top. There are some points in the point cloud that are pretty sparse or low density in data, and that just may be due to the resolution of the angles. Furthermore, you can notice that the lines are at an angle, and that was mostly due to the fact that the laser was glued in at an angle. It was calibrated with the camera, but that just resulted in angled returns. This data can then be compared with the actual pictures. So you can overlay the point cloud on top of images of the bend, as you can see here. It lines up pretty well. You can see that the planar faces of the cube line up. However, one thing is that the point cloud is slightly distorted, and that just may be due to the calibration. If the cube is lined up on the bottom for the base, the top is slightly angled into the counterclockwise position and doesn't exactly line up with the trestle. You can also see it from a front-on view. Same thing, if you line up the top trestle part, it seems that the base is scaled down, and that may also just be due to the calibration and just how the tripod was placed. Overall, though, it matches the profile pretty well of the bend. There's some noise here and there, but it doesn't seem to be rather erroneous. Once the final text file has been created and all the relevant data stored to a single file, this file can then be imported into some sort of mesh software to create a mesh. How that's done is you just select the file of relevance. In this case, I use a space as a delimiter, and you import it. So this is the resulting point cloud, the same thing we saw in the MATLAB image, but just now in the software called MeshLab. So from this, you can then go ahead and create the normals. The normals just basically look at neighboring points and determine what the theoretical surface would be. And from there, it just creates a normal relative to that surface. So you can choose the number of neighboring points to consider. I chose a rather large number just to have higher accuracy. The smaller numbers were resulting in a lot of distortion. So once you set that and apply the normals, you can then go ahead and do a Poisson surface mesh. And that, I just set all of the characters as default. I didn't change anything. And I just went ahead and created a mesh from that. So after that, you can then go ahead and start deleting faces that you believe are no longer relevant. That process is pretty straightforward, and you could just cut away meshes that you think should not be there and are not pertinent to the overall profile of the design. The resulting mesh then looks like this over here. So when using MeshLab, the mesh turns out to be pretty two-dimensional or planar, and there are a lot of areas that are not exactly connected. So you can see that the top trestle is not connected to the base, and like I said, that's mostly due to the low density of the actual data set. Overall, though, it's still pretty discernible as the tau beta pi bent and turned out to be a pretty solid mesh. I also decided to try it around in Cloud Compare. So Cloud Compare also created a mesh that looks exactly like the bent profile for the most part. However, the mesh here doesn't really connect the data set as well as the mesh in MeshLab did. It does add more volume with regards to the base. You can see that it does take into account the depth of the point cloud, but there's a lot of sparse regions, especially when you look at the two sloping members of the upper trestle part.